Hello, Discrete Mathers. This is the series of mini lectures for Wednesday, March 18th. I do think I'm getting the hang of Zoom a little bit more. I know how to incorporate more of its features. I can go back and forth easily between doing this sort of thing, showing you something I'm looking at on my screen and incorporating board work in a relatively seamless way. And I think that Zoom is much higher quality. It's less grainy, it's less glitchy. So I think I'm gonna move to this format perpetually from this point on. So, and the meeting should go more smoothly. So hopefully you'll consider attending those. I'm not going to force you to do that, but I think it'll be good for you to come and listen to questions that people have. But again, I'm going to have a permanent record of the lectures themselves in here and use the Zoom time for answering your questions about lectures and whatever else. Okay. So, yeah, that's just kind of the plan moving forward. There's no office hours tomorrow morning. But we will have a Zoom session, and once I post these lectures, I'll send out an invitation to that. Okay, so all right, so it wouldn't be totally it's being the coronavirus era, and me being a mathematician and enjoying numbers. Hey, let's have a little update on the coronavirus, all right? So here we go, you ready? So here is a screen that I really think is kind of interesting. This comes from the Johns Hopkins University. They've been tracking data very, very carefully. This is the thing I check out. I don't know if you've seen it before. I check this out usually a couple times a day. They update data throughout the day. And so as you can see here, this kind of just puts things in perspective. I mean, listening to the media, you can tend to get yourself into a panic. There's a lot of shrill voices out there. But and this looks bad because they have these big giant red dots everywhere, but if you kind of zoom in, you'll get a little bit of perspective. So like here's Ohio right here, right? And if you click on Ohio, you can see that there are 52 confirmed cases, okay? And they always are keeping track of it, the number of active, recovered, and those that have died so far. Okay, so that's kind of interesting. So again, if you go over to China, it's like, man, look at that giant red blob right there, yeah. But of course, they've kind of gotten through most of it. So this is from the Hubei province in China. 68,000 confirmed cases, 3,000 deaths, and 56,000 have recovered, and a little bit under 9,000 current cases that are still going on. Those death tolls are probably inflated in terms of a mortality rate because they definitely don't know everybody that had the virus, okay? So that's one thing to keep in mind. I'm just trying to give you some optimistic things to think about here. The other thing I would say is there's some unusually large dots in the United States. So there's 1, 2, 3 big ones. So there's Washington at 904, 904. Okay, there's California at 589, okay, and I think New York is a pretty big one. So New York 1,700, yeah, wow, man, what's going on here? Okay, so New York's at 1,700. Okay, and that's a total of 3,193 cases accounted for between those 3 states. And if you look over here on the left, the U.S. total has 5,702 cases, 52 of which are in Ohio. 5,702 cases. 3,193 are accounted for among those 3 states. So that's kind of interesting, and kind of puts things maybe a little bit in perspective. The other thing I would say, so look right here, you have the US and you have Switzerland are kind of right next to each other on here. Switzerland's has a little bit less than half the number of cases of the US, but of course, where is Switzerland? Well, it's like, it's like right over here, it's tiny. Where is it? Is it Switzerland? Where am I even looking at the right place? I thought I was. Is that it? Yeah, rather it is right there. Switzerland's right there. Okay. So look how tiny that is. Let me zoom back out. It's right there, right there above the boot where they've been having a lot of issues there. But that's tiny, right? That's a tiny country. And they have about 8.5 million population in Switzerland, okay? About 16,000 square miles of land mass in Switzerland. Okay, so again, they have about actually it's about 8.6 million in Switzerland and about 16,000 square miles of land mass. Okay, the United States is about 3.8 million square miles of land mass. So, I mean, 3.8 million square miles versus 16,000 square miles. That's 246 roughly times more land mass in the United States. Okay, and secondly, there's about 8.6 million in Switzerland spread over those 16,000 square miles. Okay, we have about 330 million in the United States. That's 38 times as many people in the United States, but we're spread over an area that's 246 times larger. Okay, 246 times larger than Switzerland. So that's something to keep in mind. We have less population per square mile. Okay, so that's something to kind of have hope in, and to not get overly panicked about. So, the measures that we've been taking seem prudent, of course, but things maybe aren't as horrendous as they might seem, perhaps. Okay, so this graph over here is interesting. Okay, this is kind of the total number of cases that in mainland China over time. Looks like sometime in the middle of February, it was starting to explode, and then they really took some extreme measures, and they were able to bend this curve down. We call that an inflection point in mathematics. There's kind of the inflection point is back here, and then this thing started to level off over time. You can see the green is the number of recovered total around the world, most of those in China at this point. And here is other locations. You can kind of see this thing was trending. It was like, oh man, here comes the exponential explosion, like a few days back. And lots of countries started taking more and more extreme measures. I think, if I'm looking at this right, it looks like we might be at, kind of like an inflection point, somewhat like what was going on here. So hopefully this thing will level off. This thing will level off over time. Okay, and another thing I would mention is China. It's sort of interesting. China has a land mass that's about the same size as the United States. Okay, and that was the epicenter of this whole thing. They ended up, look right up here, it's about 81,000 cases. The United States is currently at 5,700. Okay, 5,700. So we have 330 million people in the United States. China has a little over 1.4 billion. They have about 4.25 times as many people as us, jammed into the same amount of land mass. Okay, so that's something to kind of keep in mind as well. So if the disease spread at kind of the same rate as it did in China, you would expect, roughly about a quarter of the number of infections that we saw in China. Okay, so I don't know, maybe 19 or 20,000 or something like that. It will be interesting to track that over time. So anyways, just kind of wanted to point that out at the beginning. So that's cause for, I guess, optimism in some cases, and that's just a little daily briefing on the coronavirus situation. We're at about a little over 190,000 worldwide confirmed cases. Okay. All right. So let's talk about discrete math. Yeah. Hey, let's do it. Okay. So let me pull this up. Today we're talking about independence. Okay, independence. And here we go. So independent events, what are they? Now I will tell you that whenever I'm evaluating a textbook for whether or not I will or will not use it, one thing I always do, okay, so like as a professor of mathematics, I oftentimes will get sent free copies of textbooks, okay, to evaluate for potential use in my classes. And the first place I always turn is the discussion about independence, because there are certain things that if you say certain things wrongly, you will end up really kind of messing up people's thinking in terms of what's going on with independence. Okay, so let's talk about independence a little bit. What is it? Okay, what is it? Now, the definition of independence is a little bit more complex than, the way we talk about independence in English. So when I say independent, if I say that, this is independent of that, you tend to think that they have no influence over one another whatsoever. That's not really the sense of independence when we're talking about probability and talking about two events being independent from one another. What's going on is the following. So we just talked about conditional probability before, okay? So A and B are independent from one another if the probability of A given B is equal to A. What that means is that given the information that B has occurred, the probability that A is now going to occur is no different than it was at the beginning. That's what that equation says. Let me say that again. If I tell you that the event B happened, then the probability that A is going to happen does not change. It's the same as it was without the information that B happened. That's what independence means, okay? So it means that given that B happened, the probability that A will happen is the same as it was at the beginning. That's what independence means. Let me tell you what independence does not mean. It does not mean that A and B have no influence over one another. Indeed, the one event might deeply influence or impact the other and still preserve the likelihood of it occurring. Okay, I'll give an example of that later on. Okay, so if the probability of A given B is different from the original probability, the probability of A, then you say that A and B are dependent events. Okay, and I wrote right here, said another way, you can say that the events A and B are independent if and only if the probability of A and B is just the product of the probability of A and the probability of B. Okay, so I'm probably going to go to the board and explain that in more detail, but let me just take a peek at this. Okay, yeah, so I'm going to go over to the board. I'm going to pause this and we'll go over to the board and do a little bit of work. All right, so we said that events A and B are independent if the probability of A happening, given that B has already happened, does not change the probability that the probability from what it was at the beginning. Namely, it's still just the probability that A would have happened. Okay, so A and B, events A and B are independent if and only if, okay, the probability of A given B is equal to the probability of A. So B's occurring does not change the probability that A occurs. It's still the same as it was at the very beginning. That's the essence of what is being said here. So, but I want to make a couple of notes here. So note, remember, what is the probability of A given B? Okay, well, that's the probability of A and B divided by the probability of B, right? That's what we learned when we did conditional probability. Okay, so the probability of A given B is equal to the probability of A if and only if, okay, if and only if what? This is equal to that, okay? Probability of, the probability of A and B over the probability of B, which is what the probability of A given B equals, is equal to the probability of A. Okay, well, just multiply through by B for crying out loud. So that means that the probability of A and B is equal to the probability of A times the probability of B. Okay? So again, this is equivalent to this, okay? And of course, I could also write this as the probability of B is equal to, look, I mean, I could just switch the places of A and B. So the probability of B is equal to the probability of B and A. I'm just kind of writing this differently over the probability of A. Okay? All I'm doing is just shuffling this thing around, right? And this holds if and only if what? What is this? This is the probability of B given A. Okay, so this is the same as saying that the probability of B given A is equal to, this is the probability of B given A. It's equal to the probability of B. Okay, so this, all of these things are saying the same thing. All of these things have to be simultaneously true. Okay, probability of A given B is the probability of A. Probability of A and B is just the product of the probabilities. Probability of B given A is just the probability of B. Okay? In essence, all of these things are basically saying that the occurrence of either of those events does not change the probability of the other event happening. That's what independence means. It does not mean that they do not influence each other. Now, here's the thing though. If the events don't influence each other, that implies that they are independent. That is, if they don't influence each other, they will be independent events, yes. But it doesn't go the other direction necessarily. That is, if two events are independent, that doesn't necessarily mean that they don't influence each other. Okay? So kind of store these three identities in your mind. Okay, store these three identities in your mind for a minute. I'm going to go back to the presentation though here, and we're going to talk through some more stuff here. Hang on a sec. Shoot. Okay, so screen. Yeah, here we go. Okay. All right. So, all right. So said another way, that, and incidentally, I could also have said the probability of B given A is the probability of B, right? So that's also behind me on the board here. But we just talked about that. Okay. The events A, B, and C are mutually independent if and only if the following two conditions hold. Okay. So first of all, each pair is are independent events. Each pair of events out of A, B, and C are independent, which we've already said I can say that as like the probability of A and B is just the product of the probabilities. Similarly for the other two, this thing is spilling off the end of my slide here. That's all right. But also the probability of A and B and C is just the product of those probabilities. And by the way, you know, that also makes sense. So let's think about this, okay? So let's go up here on the board and I'll show you. Let me erase this, okay? So think about this. We're kind of becoming experts in doing conditional probability computations. So if A, B, and C are independent, that implies the following. So what would the probability of A and B and C equal? Well, we were doing a computation like this yesterday in the Zoom session and in our lecture as well. So that's like the probability of A, right? So we say, okay, if I want A and B and C to occur, then A needs to occur, yeah? But then B needs to occur given that A has occurred, yes? And then, right, this is just true even if A, B, and C weren't independent, but in a minute we're going to invoke independence, okay? So this, what I'm writing right now is true no matter what. So at this juncture, both A and B have happened. So the next factor would be the probability of C given that both A and B have happened, okay? And because of independence, we know that the probability of B given A is just the probability of B. Yeah, so this is going to be the probability of A times, it's like, well, A's occurring should not influence what the probability of B is. Okay? Even though I'm zooming in to the new sample space A, B, the probability of B occurring is still the same, even in that zoomed in place. Okay, so this is times the probability of B. Now, if A, B, and C are independent, then A and B occurring, that shouldn't have any impact on the probability that C occurs. The probability of C should be the same as it was at the beginning. So it should be times the probability of C. Okay, which is why A, B, and C independent means that the probability of the intersection is just the product of the probabilities. Yeah. Okay, so the conditioning ends up kind of going away when you have independent events. Okay, so let's go back in here. Okay, yeah, all right. So, okay, so here's this little factoid. Okay, if you are independent, if A and B are independent events, then I claim that any combination of like complements and of those things are also going to be independent. Okay, so that's kind of interesting. And by the way, you could say this about more than two events. You can say it about lots of, 3 events, for instance. And by the way, on the last slide, again, it's very important you can't just check that to check that 3 events are independent. It's not enough to just check that the probability of the triple intersection is equal to the product of the probabilities. You also have to have pairwise independence of events. Okay, it's possible to cook up examples where you have probability of the triple intersection is equal to the product of the probabilities, and yet something goes wrong on the level of 2 events. Okay, so going back over here, let's check this right here. So if events A and B are independent events, then the following pairs of events are also independent. Okay, so let's see what I want to do. Let's go on the board here. I want to show that we have lots of independence. Okay, So okay, if A and B are independent, then you know this is true. This is just the probability of A times the probability of B. Okay, this is one way to characterize independence. This is one way to do it. We saw that we could do it with conditional probability. We could also just check that this is true. Okay, so if this, then what? Then what? Okay, then what? Okay, well, what about the probability of A prime and B? Okay, the probability of A prime and B. Well, well, okay, that is the same. Let's just say, what if I were to add in the probability of A and B? So think about this. What's this equal to? The probability of A prime and B plus the probability of A and B. Let's sort of draw a picture of that, okay? So here's the sample space. Here's A, here's B, okay? The probability of A prime and B, okay? So this right here, that's A prime and B. Okay, and where is A and B? Well, that's right here. Okay, so this is A and B. Okay, so if those are disjoint things. And if I add them together, what do I get? Well, you get the probability of B. Yeah, so this is just the probability of B. Okay, so you have this. So the probability of A prime and B, well, that's equal to the probability of B minus the probability of A and B, okay? But what do I know about the probability of A and B? Well, it's the product of the probabilities. So this is equal to the probability of B minus the probability of A times the probability of B. And what can I factor out of that? Well, I can factor out the probability of B. So I'll just write this as the probability of B times 1 minus the probability of A. Okay? Which is what? 1 minus the probability of A, that's the probability of A prime, for crying out loud. Okay, so that's just the probability of A prime times the probability of B. So look at what we've shown here. This guy is equal to this. Yeah? Probability of A prime and B is equal to the probability of A prime times the probability of B. So what does that tell you about A prime and B? That means that A prime and B are independent. Okay, they are independent. Okay, so if A and B are independent, then A prime and B are independent, okay? And I'm telling you that it's going to be no problem to get the other ones from that, okay? So like A and B prime, A prime and B prime, those are all going to be independent of each other, okay? So there you go. So let's go back in here, okay? All right, so I'll leave the other ones to you there, but it's not that different from what I just did for A prime and B. But if two events A and B are mutually exclusive, that means the one event occurring excludes the possibility of the other one occurring, and both have positive probability, then they are dependent. Yeah. Why? Well, that's fairly easy to explain because watch this, okay? So mutually exclusive means if the one event happens, it's impossible for the other one to happen. Remember that example I was giving about queens and hearts? I was saying things like, I was saying things like, you know, if I draw one random heart and I tell you that, or one random card and I say it's a heart, and then I say, what is the probability that I'm holding the Queen of Spades? You're going to immediately say 0. That's because the event get a heart is mutually exclusive with the event get the Queen of Spades, okay? So they are dependent. Let's kind of see why that happens to be the case here briefly. Okay, so erase this. Okay, so again, independence means this thing that's at the top of the board. Okay, so what we're saying is if A and B are mutually exclusive with we said that the probability of A greater than 0 and the probability of B is greater than 0, right? So that there's something going on with each one. Then what about the probability of A given B? Okay, so if B has occurred, can A happen? No. So this probability is 0, which is less than the probability of A. Yes? So look, in order to be independent, this conditional probability has to be equal to the probability of A. So what? So A and B are dependent. Okay, and that makes sense. I mean, they're dependent in a very strong sense. The one happening excludes the possibility of the other occurring at all. Okay, so that's interesting. Okay, so moving on. Okay, A and B mutually exclusive means they're dependent. Okay. All right, so let's look at this example right here. I think maybe, let's see here. Yeah, okay, with a couple of examples here and we'll be done. I think I'm just gonna go ahead and finish this thing off, okay, in one lecture. I like the way that Zoom works better here. Okay, so an oil exploration company currently has 2 active projects, one in Asia, the other in Europe. A is the event that the Asian project is successful. B is the event that the European project is successful. Okay, so, all right, yeah. Okay, it would make sense that those 2 events, all things considered, would be independent. I mean, you're in 2 completely different parts of the world. Okay, so we're going to suppose that A and B are independent events. The probability that we're successful in Asia is 40%, and the probability that we're successful in Europe is 70%. It says, okay, so and we're assuming that A and B are independent. If the Asian project is not successful, what is the probability that the European project is also not successful? Okay, so if the Asian project is not successful, okay, so that's something we're given. So we're given that the Asian project is not successful. Okay. Okay. Okay, so if the Asian project is not successful, what's the probability that the European project is also not successful? Well, I mean, I'll write this up on the board here because this one's fairly easy. So we're being asked for the probability of B prime given A prime. Okay, so the probability of B prime given A prime. Okay, so because we're given that the Asian project was not successful. But if A and B are independent, so are B prime and A prime. Yeah, B prime and A prime. So that would mean that this would just be the probability of B prime, which would just be would be 30%. Yeah, because the probability of B was 0.7. Okay, so that one's kind of easy now that we know what's going on here. what is the probability that at least one of the two projects will be successful? At least one of the two projects will be successful. Okay? So that means, in fact, I'm going to kind of leave that even in this small screen right here, because this one's going to be fairly easy as well. In part B, we're being asked, okay, for the probability that at least one of the two projects is successful. That means A was successful or B was successful. So that is the union of A and B. We want the probability of A or B. Okay? So that would be the probability of A or B, which we know how to compute. That's the probability of A plus the probability of B minus the probability of A and B. But we know what the probability of A and B is. It's the probability of A times the probability of B. So this is going to be the probability of A plus the probability of B. Expand this a little bit. Let me expand this a little bit. Yeah, let's do that. Yeah, okay. Okay, so the probability of A plus the probability of B minus the probability of A times the probability of B, because the probability of A and B, that's, those are independent, okay? And I know what these numbers are. They're 0.4, 0.7, and I just have to multiply this. This is 0.4 plus 0.7 minus 0.4 times 0.7, okay? I don't know, we'll just write this down. This is 1.1 minus 0.28, okay? 0.28. Okay, so what would that be? 0.82 or something, okay? Okay, so that's the probability that at least one of the two projects is successful. Okay, 0.82. I think that's it. Yeah. Okay, because yep. Okay. Given that at least one of the two projects is successful, what is the probability that only the Asian project is successful? That only the Asian project is successful. Okay. So what are we being asked to do on this one? So let's see. Let me expand this out a little bit. Okay. Okay, so given that at least one of the two projects is successful, what is the probability that only the Asian project is successful? Okay, so what we're being asked to do in this one, so at least one of the two projects is successful, that's A or B. What is the probability that only the Asian project is successful? So here, we want the probability, okay, we're given A or B, okay, which we just computed, okay? And we want only the Asian project is successful. Only, the probability that only the Asian project is successful. That means A and B prime, okay? A and B prime, okay? Well, that's interesting. We just have to remember that this probability we just computed for A or B is 0.82. Okay, but let's take a look at this. So this is the probability of what? The probability of A and B prime intersected with A union B. Okay, close parentheses. I went this intersected with that. Okay, divided by the probability of A union B. Okay, and I can like distribute this intersection over this union. Okay, so this is equal to what? The probability of let's be careful here. So it's going to be A intersected with B intersected with A. A intersected with B intersected with A, but A intersected with, or A intersected with B prime intersected with A rather. But A intersected with A is just A. So this is going to be A intersected with B prime, union, okay, so A intersected with B, and I'm distributing this intersection over this. What's the union of B prime and, or what's the intersection of B prime with B? Well, that's the empty set, right? Over the probability of A union B, okay? And so this is just going to be the probability. Look, if I union this with the empty set, that's just this event right here. It's the probability of A intersected with B prime divided by the probability of A union B. Okay, running out of room here, but that's all right. And A and B prime, since A and B are independent, A and B prime are independent. So this is going to be the probability of A times the probability of B prime divided by, we already know what the probability of A union B is. It's 0.82. Okay, and what is the probability of A? Well, it's 0.7. What's the probability of B prime? Well, that's 0.3. Okay, so this right here is 0.7. This right here is 1 minus, sorry, this is probability of A is 0.4. And B prime is 1 minus 0.7, which is 0.3. So that's 0.12 over 0.82, okay, which is, you know, basically 12 over 82, which is 6 over 41, whatever that happens to be, okay? 6 over 41 is what that probability is. Okay, and then that last question is just kind of dumb, all right? It says, suppose that instead of being independent, A and B are mutually exclusive. Find the probability of A given B. Well, if they're mutually exclusive, the probability of A given B is 0, excuse me. If B is given to have occurred, A cannot occur. Now, we just talked about that, yeah? Okay, so that's that problem. Okay, moving on. Let me move myself out of the way here. What do we have? Okay, an aircraft seam requires 25 rivets. The seam must be reworked if any of the rivets is defective. Suppose rivets are defective independently of one another. Okay, suppose the rivets are defective independently of one another, each with the same probability. Okay, so there are 25 rivets. Each one is defective with the same probability, independent of one another. Okay, if 20% of all seams need reworking, what is the probability that a rivet is defective? That a rivet is defective. If 20% of all seams need reworking, what is the probability that a rivet is defective? Okay, so they haven't given us the probability that an individual rivet is defective. They told us the probability of a seam being defective, which consists of 25 rivets. Okay, so before I kind of go into full screen mode here, I'm going to write down some information here. So I have a total of 25 rivets. Okay, so R1, R2, R25. So Ri is the event rivet I. Rivet I is defective. Okay, rivet I is defective. Okay, and okay, so what is being told to me here? The seam must be reworked if any of the rivets is defective. if 20% of all rivets, if 20% of all rivets need reworking, oh, and by the way, the probability, it says the seam must be reworked if any of its rivets are defective. Suppose rivets are defective independently of each other, okay, so they, right, there's independence among the rivets themselves, okay, each with the same probability. So let's say that the probability that rivet 1 is defective, that's the same as the probability that rivet 2 is defective. They're all the same probability. And I'm just going to call that defective probability. I'll call that P or something, okay, for the probability that it's defective. Okay, so it says, suppose rivets are defective independent of each other, each with the same probability. If 20% of all seams need reworking, okay, if 20% of all seams need reworking, what is the probability that rivet is defective? Well, here's the thing. If 20% need reworking, that means 80% don't need reworking, yes? Right? So that means that 80% don't need reworking. So I'm gonna go to full screen here and we're gonna do a little bit of computation, okay? So the probability that no rework is necessary, okay? On the one hand, that's like 80%, okay? That's 80%. But don't you see that that is also the probability that rivet 1 is not defective, okay? That's what prime means there. And what else? Well, and rivet 2 is not defective, and ... and rivet number 25 is not defective. Now, the fact that all of these rivets are defective independently of one another tells us that these events right here, all of these events are independent. Yeah, so those guys are independent of each other. And therefore, what's going to be true about all these complements? The probability of R1 prime, R2 prime, etc. Well, those are going to be all independent also, yeah? So that means I can just compute this probability by having a product of probabilities, okay? So this is equal to the probability of R1 prime, and I'm just going to multiply all of these probabilities together, okay? But like this first one is just 1 minus the probability of R1, right? And then all the ones in between, and it's 1 minus the probability of R25. But all of those probability of R whatevers, that's what I just called P up here, yeah? All of those probabilities are the same, right? So I get 0.8 is equal to, okay, 0.8 equals, okay, just to copy that down, 0.8 equals 1 minus P to the 25th power. 1 minus P to the 25th power. Okay, that's interesting. So, so that means I need to take like the 25th root of this. Okay, so 0.8. Okay, I raise that to the 1/25th. Okay, that's equal to 1 minus P. Okay, so what's P? P equals 1 minus 0.8 to the 1/25th. Okay, that is the probability of a rivet being defective. That's the probability of a rivet being defective, okay? 1 minus the 25th root of 0.8, okay? Interesting. Let's see. Those are probably the rivet is defective. We got that. It's 1 minus 0.8 to the 25th, 1 to the power 1 over 25. 25th root of 0.8, take 1 minus that. That's the probability of being defective. Okay. Okay, moving on. Show that if A, B, and C are mutually independent, then A and the intersection of B and C are also independent. Okay, and this will be kind of the last thing that we do here. Okay. All right. So if A, B, and C are mutually independent, then A and B and C are independent. Well, actually, that's sort of easy, okay? Because remember, if A, B, and C are mutually independent, that means that I can take any pair of events and they're going to be independent, yes. And the probability of the triple intersection is the product of the probabilities. Okay, so okay, so watch. What about the probability of A and B and C? Okay, well, okay, so I put B and C in parentheses right here as if it's like one event, but this is just the probability of A and B and C, of course, which since A, B, and C are independent, so A, B, C independence allows me to write this as the product of the probabilities. Yeah. But B and C are independent. Yeah. We have pairwise independence. B and C are independent. So the product of the probabilities is equal to the probability of the intersection of B and C. So this is equal to the probability of A times the probability of B and C. So overall, we see that the probability of the intersection of these two events, right? Here's the one event, and here's the other event. The probability of the intersection of those two events is equal to the product of the probabilities of those. And that means that A and B intersected with C are independent, right? So A and B intersected with C are independent. Okay? Okay, makes sense, hopefully. All right, that's it. I'm going to post this. I'm going to send out a Zoom invite for tomorrow afternoon. You know, again, remember, I'm going to post a quiz. I will probably post a quiz tomorrow, and you'll turn it in on Friday. You'll upload it the way that you uploaded the last quiz, and your quiz will be one of the problems that we've worked on up to this point. Okay, so we just finished independence. And I'm going to talk about Bayes' theorem on Friday, and then I'll start in on some random variable stuff. Okay, and we'll be getting close to statistics at that point. All right, so I'll post a homework quiz tomorrow, and we'll have a Zoom session where you can ask questions about this lecture. But other than that, that's it for now. All right, see you later.